Okay, guys. So today we will begin section B of our course. So it's constraint optimization. We begin with today's lecture, convexity theory, convex sets and functions. So we'll define a ball first. A ball with center C and radius R is this set X such that the norm of X minus C, that is the distance of X from C, is less than equal to R. The set of all such points X is the ball. Here is an illustration of a ball. C is the center and R is the radius. All the points on this hypersphere or inside it are included in the ball. Now, if X is an element of any set S, then it is in the interior of S, where S, the set S is some subspace of an n-dimensional Euclidean space. It's in the interior if or for any delta, no matter how small, delta could be very small, a ball centered around X and with this tiny radius delta will always belong to the set S. Then X is said to be in the interior of S. So this is S, the region S, and X is in the interior of S if and only if we can surround X by a ball with X as the center of some radius delta, and delta can be arbitrarily small. Int S is the set of all interior points of S. So it's the boundary of S is not the interior. Everything else is in the interior. Okay, so this straight line segment, A is less than X is less than B, is in the interior of, well, this is the interior of the closed straight line segment. A is less than equal to X is less than equal to B. Interior of this ball here with center C and radius R is the set of all points X such that the distance from X to C is strictly less than R, not less than equal to R. So that's what we mean by the interior of a region S. Convex combinations of points. Let theta be a parameter in this closed interval 0 and 1. Then theta x plus 1 minus theta y is a convex combination of the points x and y. Let's see. When theta is 1, then what happens to theta x plus 1 minus theta y? It's equal to x. See, theta can be anywhere in this closed segment between 0 and 1. So this is this theta x plus 1 minus theta y. It's the point x itself, when theta is 1. When theta is equal to 0, then theta x plus 1 minus theta y is equal to y. So this convex combination of x and y with theta equals 0 is this point y itself. Now with theta equals half, the point becomes x plus y divided by 2, which is the midpoint of x and y. Okay, so for all values of theta between 0 and 1, this convex combination, this green circle here, will lie anywhere in this straight line connecting the points x and y. Okay, it won't go outside on this side or outside on this side. It'll lie in the segment, straight line segment, that is this red line, which connects x and y. Okay, so let's define a convex set. So for any theta between 0 and 1, we consider theta x plus 1 minus theta y, where x and y are 2 points in this convex region. This green colored region is a convex region, and I take any 2 points. Now I've taken 2 extreme points in the boundary, but I could have taken any pair of points x and y. Then the convex combination of them must lie in this straight line, connecting them, that's a red line, correct? And if any convex combination of x and y, as long as x and y lie in the region C, as long as every convex combination also lies in C, then we say that the region C is a convex region or a convex set. Okay? In other words, take any pair of points x and y that lie in the region and then connect them together with a straight line. And if the entire straight line lies inside the region, then we say that the region is convex. Here is an example of a strictly convex region. Now, this is convex, but this is not strictly convex. Okay, because this straight line doesn't lie in the interior of C, this region C. But here, if we take any pair of points, excluding theta equals 0 and theta equals 1, if every other point lies in the interior of this region, then we say that the region C is strictly convex. Any questions so far? And this is a non-convex region. When we take any pair of points in the region C, we must have all the convex combinations of the 2 points being in the region C itself. If that is violated, then the region is non-convex. Here, for some values of theta, the convex combination of x and y is outside this region, green region C, although x and y are both inside. So this is not convex, this is convex, and this is strictly convex. Okay, normal to a hyperplane. So this, what you see here is a hyperplane. It stretches to infinity in this three-dimensional space. This is a hyperplane, and A is a normal vector. So this vector A is orthogonal to the hyperplane. Now we normalize A so that it becomes a unit vector. So this A hat is a unit vector that's orthogonal to the hyperplane. Now we take any point X, this is X, this blue point X, on the surface, on the hyperplane, on this surface, which is the hyperplane. Okay, so this point X is on the hyperplane. What does it mean? A transpose X, which is a projection of X along this direction, A hat, this will be on the hyperplane too, right? It will be a constant. All these points, A hat transpose X equals constant will lie on the same hyperplane. Okay. Now, this distance of this point X from the hyperplane is this constant, which is alpha. I express this as alpha divided by the length of A. Okay, so the equation of the hyperplane can be written as A hat transpose X equals alpha over length of A, but given A hat equals A divided by length of A, this implies A transpose X equal to alpha, where alpha is some constant. Okay, so this A transpose X equals alpha is the expression of a hyperplane. All these points X will satisfy this condition equality as long as it lies on the hyperplane. And the distance from the origin to the hyperplane is alpha over L2 norm of A, length of A. Okay? So that's the equation of a hyperplane. A transpose X equals alpha. The length, so alpha divided by the length of A is this distance. That's the distance of the hyperplane from the origin. A transpose X equals alpha. So alpha divided by L2 norm of A. Okay? Now, this X satisfies A transpose X equals alpha, so it lies on the hyperplane. Now, suppose we have another point X such that A transpose X is less than alpha, then it lies on one side of the hyperplane. You see this point X? It's on this side of the hyperplane. It's called a half space. Okay, so this point X is on the half space that includes the origin. Now, A transpose X greater than alpha, if there is such a point X, A transpose X is greater than alpha, then it lies on, the point X lies on the other side of the hyperplane. Okay? Okay, now back to definitions. So a hyperplane, A alpha is the set of points X such that A transpose X equals alpha. And half spaces are set of points X such that A transpose X is less than equal to alpha. Note that this includes the hyperplane itself. And another half space is A X such that A transpose X is greater than equal to alpha. Okay? Convex combinations of K points, X1, X2 until Xk in n dimensions. Suppose we have K points in n dimensions. Okay. Then their convex combination is any point Z, which can be expressed as a linear combination of the Xk's, X1, X2 until X uppercase K. Okay, so Z equals summation K, theta K, Xk, where theta K is the weight attached to the point Xk, and all these theta Ks must be strictly greater than equal to 0, not strictly. They must be greater than equal to 0, and summation of over all Ks of theta K should equal 1. The set of convex combinations of points is called its convex Hall. So here we have how many points? We have X1 through X7, 7 points. And this blue region, including the black boundary, is this set of all convex combinations of these points. And that's called the convex hull. It will always be convex. In fact, you can easily show that if 2 points Z1 and Z2 are convex combinations of these x's, then any linear combination of Z1 and Z2 with theta Z1 plus 1 minus theta Z2 will also lie in the convex hull. That's how you prove that this convex hull is indeed convex. Okay, I'll skip the supporting hyperplane and the separating hyperplane theorems because in this version of our course, 840, we don't need these definitions. I keep changing the course contents every year a little bit. Okay, we won't need the separating hyperplane theorem either. Okay, so now let's move on to convex functions. Suppose F is a convex set. Sorry, excuse me, the domain of F is a convex set. And X and Y belong to the domain of X. Okay, and then given any theta between 0 and 1, F of this convex combination of X and Y. X and Y are 2 points in the domain of F, the function F, which let's say it's a convex function. This is a definition of a convex function. Okay, for a convex function, the domain must be a convex set, by the way. And so I take any 2 points in the domain, theta x plus 1 minus theta y, and f of that theta x plus 1 minus theta y should less than equal theta fx plus 1 minus theta fy. So f of theta x plus 1 minus theta y should be less than equal to theta fx plus 1 minus theta fy. That's the condition for the function to be convex. Here is an example in where the domain is one-dimensional. So I take a pair of points, x and y. Okay, let's look at the left-hand side first. This is theta x plus 1 minus theta y, this point here. So this ratio of this segment to this segment is, so this is 1 minus theta is to theta. Okay, so that's why this point is theta x plus 1 minus theta y. And this is f of the function f. Okay, so this is x, this is f of x. This is y, this is f of y. And this is theta x plus 1 minus theta y. And so this is f of theta x plus 1 minus theta y, which is the left side. Okay, so this is the left side, what I have on the left side. Okay, it's this here, f of theta x plus 1 minus theta fy. Now let's try to find what's on the right side. This is x and this is y. This is fx, this is fy, correct? Fx and fy. Now observe here. No, I don't have it. Anyway, so this is theta fx plus 1 minus theta y because the ratio of this straight line segment to this straight line segment is theta is to 1 minus theta. Same as this. So I've divided this straight line joining x fx and y fy into this ratio. This is 1 minus theta, and this is theta. Okay, this ratio is the same as this ratio, and which is the same as this ratio. Okay, so this is theta fx plus 1 minus theta y, which is this one, the right hand side. And this we saw earlier was f of theta x plus 1 minus theta y. So you can clearly see that this f of theta x plus 1 minus theta y, which is this one here, is less than equal to theta fx plus 1 minus theta fy. That's why this is a convex function, shaped like a cup. Strictly convex function. So theta can be anywhere between 0 and 1, including 0 and 1. But if theta is strictly less than 1 and greater than 0, and then we replace this greater than equality with strict, it's less than equal, with strict less than, then that gives us the definition of a strictly convex function. Any questions?
Yes, Dr. Das, I have a question on this less than or equal. I'm just wondering, when does this equality holds?
Well, suppose you had something like this, a cup shape with a flat bottom.
Yeah.
Then it will hold with an equality. If I'm not clear, let me. So suppose this is my function. This is flat. Okay.
Yeah.
Sorry that I drew this, and then like this. So this is not strictly convex because it's flat here, but it is convex. If I take any 2 points x and y in this flat region, horizontal flat region, it might not be horizontal either, but if I take any 2 points x and y, and I join them, it will be equal. The convex combination will be equal, right?
Yeah.
Okay, so back to here. So that was the case where it wasn't strictly convex, but it was convex nevertheless. And we can define concave functions, concavity in exactly the same manner. Function is strictly concave if negative of the function is strictly convex. A function is concave if its negative is convex. This is a non-convex function. Okay, so we have some point here which does not meet this condition, like here. So this is a non-convex function. F of theta x plus 1 minus theta y is more than theta fx plus 1 minus theta fy. Okay. Now let's move on to differentiable functions. Here is a function over x and y, f of xy. It's a function of this x is a vector, right? This x, bold x, is a vector, and x and y are its scalar components. So f of x belongs to R. This is the z-axis. The z-axis is the range of this function, and x and y. So this xy plane is the domain. Okay, and now On the xy plane, this is, I plot the function. I project the function onto the xy plane. Okay, this. And so this is where it's a minimum, right, at this point. And then as you go further out, the function increases. Minimum, any direction you go out, the function increases, f of x. And then I switch to the top view. So this is x and y, and this is this same, since this is at an angle, that's why its projection, this is looking like a ellipse. It's in fact this circle. Okay. Now, del f of x is a vector in this xy plane that in this direction. This is the del f of x, the derivative of f of x. Okay. So this is del f of x, and it's defined as partial f over partial x, partial f over partial y. It's a two-dimensional vector. And these concentric circles that you see are called level sets. Each of these contours represents f of x equals some constant for different values of the constant. Maybe the constant is, this was the minimum, right? Maybe it's 0 here at the center. F of x is 1 in this circle. F of x equals 2 here. F of x equals 3, 4, 5, 6, and so on. Okay, maybe that's how it is. And so these concentric circles are called level sets. And this is the gradient at this point, xy. Okay, and note that the gradient is always orthogonal to the level set. That's a very important observation. First of all, it's in the direction of maximum increase of the function. That's why it's pointing this way. If you go this way, the increase in f of x is maximum. Okay, and it's orthogonal to a level set f of x equals constant. So this is another function. This is the minimum, and these are the contours for f of x equals constant for different values of the constant. Given this point x here, this is the gradient. These blue lines represent the gradient. And so this del f of x at this point x is orthogonal to this f of x equals constant. So gradients give directions of steepest ascent. And gradients are orthogonal to the level sets, these contours. Okay, any questions so far?
No.
Now, in general, when the domain of f is the n-dimensional hyperspace, then del f of x, this derivative del is with respect to x, the argument. Okay, I did not add the subscript x here, but it's implicit that we are differentiating with respect to the argument x equals this partial f over partial x1, partial f over partial x2 until partial f over partial xn. x1, x2, x3 until xn, these are the scalar components of the vector x. The Hessian, or the second derivative, is this, del square f of x, which is this, partial square f over partial x1 square, partial square f over partial x2 partial x1 until partial square f over partial xn partial x1, and so on. The last row is partial square f over partial x1 partial xn. This is partial xn over partial x1. This is partial x1 over partial xn until del square f over del xn squared. And since the order of differentiation doesn't matter, del each of these, this del square f over partial xn partial x1 is the same as del square f over partial x1 over partial xn. Okay, in other words, del square f, the Hessian, is a symmetric matrix. Okay, now let's look at, so far we were looking at scalar functions. The range was in R, just the scalar. Okay, so it took a vector as argument and f of x was a scalar. But now let's look at vector functions. That's why I have this bold f. Okay, so there are m components, scalar components of the vector, f1, f2 until fm. That's why it's a mapping from n-dimensional space to m-dimensional space. Okay, how do we define the derivative of this vector function? Now, consider any fi, any scalar component of f. We know that the gradient del fi of x is defined in this manner. It's this vector, right? The derivative of this vector function will be this matrix. It's called the Jacobian matrix. So this is the first column of the Jacobian is del f1. The second column would be del f2 and so on. The last column would be del fm. These are the gradients. Okay, so the columns of the Jacobian are the gradients with respect to of f1, f2, f3, and so on. So this is a m by, excuse me, we have x1 through xn, right? So this, how many rows do we have? N, m as in Nebraska. And how many columns do we have? f1 through fm. So we have m as in Missouri, number of columns. So this Jacobian del f of x is a n by m matrix. Okay, now let's try to find the derivative of A transpose f of x. This is a scalar. Okay, it's an inner product of f of x, which is a vector in m dimensions, m as in Missouri, and A is a vector 2 in the same m number of dimensions. So this is the inner product between the two vectors, which is a scalar. So let's try to differentiate this with respect to vector x. So this is my x. It's n-dimensional, but A and f of x are m-dimensional. A transpose f is equal to summation I equals 1 through m, because we have fm functions of ai fi of x. Correct? Now let's differentiate both sides. Del f of x is this, right? Now, del of A transpose fx is equal to, I differentiate this side, so I take summation I equals 1 through m ai del of fi of x. And this is equal to the Jacobian times A. Del A transpose f is del f of x. There should have been a parenthesis here. It's the Jacobian del f of x times A. Am I clear?
Yes.
Yes.
Okay. So this is an important expression for later. Del A transpose f of x is del f of x whole, del f of x times A. We'll need this later, maybe in the next lecture. Taylor series expansion of multivariate function fx plus delta x equals fx plus summation I partial f over partial xi del xi plus half summation I summation j del square f of x over partial xi partial xj times del xi xj. Or vectorially, we can represent the same Taylor series expansion in this manner. F of x plus delta x equals fx plus del fx transpose f of x, del x plus half del x transpose del square f of x, that's the Hessian delta x, plus error terms, which is order delta x norm cubed. Or if we let y be x plus delta x, then this delta x is replaced with y minus x, and so you get this form of the Taylor series expansion. They all mean the same thing. Okay, and the Taylor series expansion of the gradient. So del f x plus delta x gradient is del f of x plus del square f of x delta x plus error term. Okay? Okay. Convexity of a differentiable function. We looked at differentiable functions and we saw what the gradient was. If the function is differentiable, then we have its gradient. So it's f of x is a convex differentiable function. That means that if it's convex, then this must hold good. Fx plus del f of x transpose y minus x must be less than equal to f of y, given any 2 points xy in the domain. Now, instead of showing this for n dimensions, let's look at scalars. Okay, we justify this expression in terms of scalars. So, if x and y are 2 points scalars, and f of x is a univariate function, x is a scalar. So this function is convex if this condition is met. F of x plus derivative with respect to x of f of x times y minus x must be less than equal to f of y. Illustration. Okay, so this is the domain x, y, r in this x-axis, and then this is f. So I take a point x, this is f of x. I take another point y, oh no. So I draw a tangent to this curve at x, and this is the tangent. This straight line here is the tangent to this curve. Therefore, the slope of this tangent is equal to the derivative of the function, right? Okay, now let's take another point y. Now, this is y. I take the projection onto this tangent, and then I want to find out what's this point here, what's this here geometrically. Now, if you look at this triangle here, this is what? y minus x. This gap here is y minus x, right? And this is tan theta, where theta is this angle. The slope is tan theta. Therefore, this gap here is y minus x tan theta, which is y minus x times the slope. So this gap here is slope times y minus x. And this is f of x. So this here, which is this gap plus f of x, is this. F of x plus slope times y minus x. Okay. And so here you see, so this is this point here. F of x plus partial over partial x, f of x times y minus x. So this is the left-hand side of this inequality, this here. Now what's f of y? This is y. What's f of y? This point here, right? This is f of y, the right side. And you can see that f of y, this is a convex function. And so f of y is more than this, the expression on the left. Are you guys clear with this?
Yes.
Okay, and so this is a requirement for the function to be convex. This is for convexity, convex functions in terms of the first derivatives. Okay, now let's turn our attention to second derivatives. So I have x belongs to domain of f. The function f is convex if its Hessian del square f, the second derivative, is positive semi-definite. And it's strictly convex if the Hessian is positive definite. Okay, now coming back to scalars, what's the second derivative of this? The first derivative is negative here, right? And then somewhere around the minimum, very close to this actually, it's flat, 0. And then it's increasing. So the derivative of the function is negative here, and then it becomes positive, right? So the derivative of the function is increasing, which means that the second derivative must be positive, right, in scalar terms. So for scalars, positive is the same thing as positive definite for a matrix. So if this were a scalar, x were a scalar, then this would mean the second derivative is greater than 0, greater than equal to 0 for the function to be convex. And for the function to be strictly convex, the second derivative should be strictly greater than 0. Okay, and we generalize these two vector x's. Okay. Any questions?
No.
So this is the set of all convex functions, and this is the set of strictly convex functions. There will be functions which are convex but not strictly convex. Now, local minima of a function. X star is a local minimum of f of x. If there exists a ball centered around x star with some radius r such that for any x belong to this ball, that is some x which is at a distance no more than r from x star, which we say is the local minimum. Okay, so we take some point x around x star but not equal to x star, then f of x star is less than equal to f of x. Okay, so this, for all these x's within this ball, f of x, so x star gives us the minimum value of the function. So this is the ball. Outside, you can have other smaller values, smaller than f of x star. But as long as you can surround this x star with some ball, and within this ball, x star is the minimum, then we say that x star is a local minimum of f of x. Likewise, x star is a strict local minimum if we replace x belongs to this, and as long as x star is not equal to x, f of x star is always strictly less than f of x. Then x star is a strict local minimum. X star is a global minimum if everywhere, not just a small ball, okay, but everywhere in the domain of the function, f of x star is less than equal to f of x. So x star is less than equal to f of x for every possible value of x in the entire domain of the function. Then we say that x star is a global minimum. Likewise, we can have a strict global minimum. Okay, so consider this function here. This y star here is a local minimum because we can define a ball, maybe this segment here, all the way up to this point, right? Anywhere here, y star is at a minimum. That's why it's a local minimum. Okay, but it's not a global minimum. Because if you consider the entire domain, which is the entire x-axis, then x star is the minimum of the function. So this x star is the global minimum. Minima of a convex function. Every convex function has a global minimum. Every local minimum is the same as a global minimum. In other words, the convex function f does not have other local minima. It just has the global minimum. So this is a convex function. See, this is flatlined here, right? This is the global minimum. This value is the global minimum. For any x here, you get the global minimum value. Okay? Now, for a strictly convex function, every strictly convex function, f has a unique global minimum. This is a strictly convex function, and it has a unique global minimum. Next, necessary and sufficient conditions for minima. F of x is a twice differentiable function. Is x star strict local minimum? A necessary condition is its slope must be equal to 0. That's how you find the minimum, right? The derivative must be equal to 0. That's a necessary condition for a minimum, because it could be a maximum too, or it could be a saddle point. Another necessary condition is that the second derivative must be greater than equal, or must be positive semi-definite. The Hessian at x star must be positive semi-definite. The sufficient condition is that when the Hessian is positive definite. Okay, now let's illustrate why. So I take a small perturbation from x star. I'm considering x star, which is a local minimum, and delta x is a small perturbation to x star. So x star plus delta x is a point that's close to x star. From Taylor series expansion, this is equal to f of x star plus derivative of f of x star transpose delta x, this is delta x, plus half delta x transpose times the Hessian del square f of x star times del x. Okay, this is a matrix, so del x transpose Hessian del x, half of that. Okay, so this is Taylor series approximation. And we know that if x star is a local minimum, then what happens to this? The first derivative is equal to 0. Correct? So this term becomes equal to 0. So we are left with this. And we're dropping all other terms because delta x is really small. All the other terms are negligible, higher order terms of the Taylor series expansion. Okay, now if the Hessian is positive definite, then by definition of positive definiteness, del x transpose times the Hessian times del x must be greater than 0, correct? So this f of x star plus delta x is equal to f of x star plus something positive. In other words, this is necessarily more than this. F of x star plus delta x is greater than f of x star. That's why this is a sufficient condition. Okay, this is strictly great. This second term, the quadratic term, is strictly greater than 0 because this is positive definite. Now, if this were positive semi-definite, if the Hessian were positive semi-definite, then this term could be equal to 0, correct? The second term could be equal to 0, in which case f x star plus delta x is equal to f of x. So this is not a strict minimum anymore because we have this equality sign. So it's not a strict local minimum. Okay, am I making myself clear?
Yes.
Okay, and this is what I just told you. So this is greater than, because this term, if this is positive semi-definite, then this term here would be greater than 0, in which case fx star plus del x is strictly greater than fx star. And likewise, for local maximum, we have the necessary condition. This is, what if, the Hessian is negative semi-definite, then x star is a strict local maximum. Okay, and you can reason up the rest. What if del square f of x star is positive semi-definite, then x star is a local minimum, but it's not a strict local minimum. Now, what if the Hessian del square f at x star is indefinite? So it has both positive and negative eigenvalues. Okay, a matrix that's neither positive semi-definite nor negative semi-definite is an indefinite matrix. Okay, in this case, if this is the case, then x star is called a saddle point. And if it's equal to 0, then we cannot say. Now, here is an example. So these are, so that violates the, okay, this is an example which does not meet these conditions, okay, and it's a global minimum. F of x is x to the 4. So the strict global minimum is x star equals 0. But the derivative, which is 4x cubed, and the second derivative, which is 12x squared, are both zeros at x star. So those are necessary conditions, but not sufficient. This is a necessary condition. Okay, and likewise, this is a necessary condition, necessary but not sufficient condition because we have equal to 0. Now, this is for any function, and we were confining our attention to local optima. Now, let's turn our attention to convex functions. Every convex function has a global minimum. Every local minimum is also a global minimum. We saw that. And every strictly convex function has a unique global minimum. We already saw this. Now, fx, suppose, is convex and differentiable. Is x star a global minimum? Necessary and sufficient condition is the gradient del f of x star must be equal to 0. Okay? Any other questions? Any questions you have?
No.
Sure?
Yeah.
Okay. So from the next lecture, we'll do convex optimization. Today, we introduced a lot of definitions. Okay. Unless we have any questions, I'll end today.
No questions. Thank you, Dr. Das.
Okay. See you guys
Thank you.
next
Thank you.
Tuesday.
Bye.